Hi, my name is Xiuchun Kuo, and I'm joined here by Adam, Jim, Lucas, Santiago, and Teddy. Today we will be presenting our analysis and redesign on the electric skateboard. Electric skateboards are lightweight and easily deployable transportation for users to travel between two locations with minimal effort and preparation. The main power source of the electric skateboard is a rechargeable battery, making it also sustainable. We have divided our customers into primary and secondary groups. Our primary customer group is skateboard hobbyists who enjoy the speed of electric skateboard. And our secondary customer group is students and working adults who require transportation for daily commutes. This figure shows a functional analysis of the skateboard. The main function of the skateboard is to transport the user with supporting function of supporting user, controlling speed, and controlling direction. This table shows a functional component mapping matrix. The left side of the table lists all the components used in the skateboard assembly. Each part is assigned to a specific task of the supporting function from the functional analysis listed on the top. To differentiate design for primary and secondary customer groups, we have identified two modules for design changes, as shown in the first table. The bottom diagram showed the individual design for respective customer groups. The modules on the left allow skateboard hobbyists to make steeper turns at higher velocities. The modules on the right facilitate balancing for commuters while they travel through uneven terrains. Here we have the product family assembly diagram to show the delay differentiation in the skateboard assembly. A divergence occurs at the trucks and the wheels, which are the two modules we identified for differentiation in the last slide.
For designing for manual assembly, based on the assembly sequence in the product family assembly diagram, we calculated the total assembly time and efficiency for manual assembly. For a platform, we could see the assembly time of battery, screws, and nuts are relatively high compared to other parts. For module parts, we could see bearing might be a redesign opportunity. After redesigned, we could save up to 200 seconds total assembly time and increase the assembly efficiency from 0.17 to 0.33. We redesigned three parts for manual assembly, which are bearing, screws, and battery. We add alignment feature into bearing by adding a notch and groove. We eliminate the screws to minimize part count by combining screws with the risers and battery casing, which also works as alignment features. The last one is battery. We modularize original 12 battery small parts into a single subassemblies, which also decrease 36 seconds of assembly time.
For automated assembly, we decided to integrate the drivetrain subassembly where whole alignment occurs frequently. The three parts we'll be focusing on are the wheels, motor mount, and the trucks. This table shows the total automated assembly cost before design change. The insertion costs contribute to a large portion to the total cost due to difficulties of hull alignment. We'll be redesigning each part to reduce this cost. As you can see in this figure, the new wheels now have extruded cut on the inner surface so the bearing can be fitted easily without aligning the holes. The motor mount also includes a similar feature that reduces the insertion time for aligning the holes between the motor mount and motor mount clamp. Finally, the trucks now have protrusive feature for easy alignment and securing for the motor mount clamp, as highlighted in the figure. This slide shows a comparison of the subassembly before and after the design changes. As you can see, the new parts all include additional features to facilitate insertion of parts. This slide shows the total cost of the subassembly before and after the design change. While the handling cost remains the same, the insertion cost is reduced significantly by 25%. The final automated assembly cost is calculated to be $3.78 per skateboard.
Here's the manufacturing processes for the wheel, with a key dimension being a hole for the bearing fit. As is important, the bearing is snug on the wheel so it is not wobbling while riding the skateboard. After looking at the parameters for the manufacturing processes, it was determined that injection molding and machining were two methods, as discussed in the lecture, that could work for the wheel. Injection molding would be an easy way to get the exact shape of the wheel, and machining could be done easily with a machine like a lathe. Here we have the manufacturing process selection for the motor mount clamp. Key dimension is the holes for the screws of the clamp because it is important that the screws are nice and snug on the clamp so the clamp can clamp down the motor to the rest of the assembly on the board. And after looking at its parameters, it was determined that die casting and machining were two processes that we discussed that would work. Machining would be very possible to make all these holes and inlets with a lathe, and die casting would also work with this material.
For a well through the process selection, we choose the injection molding as the process method and assume the polycarbonate as the material. We only focus on the primary process and ignore the machining process, which is used to drawing the 5 standard same-size holes. In the original design, 4 holes are smaller than the middle one. Then, we calculate the cost difference between before and after following the cost formula for injection molding. First, because of the reduction of the volume, the material cost reduced almost 3%. Then we know that the operating cost for the redesigned well is 1.7% lower than the original one. And the assembly cost greatly reduced by 28% because the groove makes the assembly process easier and faster, especially for the insertion step. The symmetrical semicircular grooves can let a bearing easier to fit in comparing to only one groove or not symmetrical grooves. However, the mold cost gets higher due to the more complicated design, especially more surface patch in the redesigned well. But the total cost compared to the original design is still getting lower by 21%. Therefore, it is the suitable way to reduce the cost of the well.
The second part we selected was the motor mount clamp. Looking at the pictures below, you can see a number of ways we're able to redesign the motor mount clamp to reduce total costs and increase manufacturability. The design guidelines we followed were adding grooves for easy insertion, standardizing the holes to reduce part variety, and adding features such as the stubs in the top and bottom for orientation and alignment. Other guidelines followed were uniform wall thickness and giving radii to the internal corners. These design changes, while they did increase machine time by about 15%, they did overall reduce the total cost by 29.6% when you factor in assembly costs. This takes the part down from $8.94 to $8.51.
Having an optimized product to serve most customer needs, we can shift focus to improve the experience. We introduce a mobile application as a PSS to maintain engagement and provide enhanced features. With full customization and support, the user can tailor the ride experience to their liking and access a larger community of users. Adding Bluetooth capability allows the user to fully control the board with their smartphone, access battery and range estimate, and more. This application integrates with onboard GPS to provide enhanced safety and security features, suggesting routes and providing real-time data analytics for your trips. All of these come with reduced costs for the customer. The remote can be sold separately, the longevity will increase with future-proofing updates, and we can provide an extensive FAQ and community forums to reduce the need for support teams. Our mobile application can also help reduce our impact on the environment by suggesting eco-friendly routes to optimize battery life, offering a modular battery design and accurate life estimates to allow for quick swaps. Without the need for a physical remote, we can reduce the carbon footprint of our manufacturing process through smartphone integration. We can push complementary software and firmware updates to increase the efficiency, range, and longevity. Offer a service to buy back boards if they're past their lifetimes, to refurbish them and keep them away from our landfills. And offer a pickup and repair service to extend the life cycle of the boards. In conclusion, our redesign of the electric skateboard has resulted in a hobbyist board for thrill seekers and a commuter board for fast and easy transportation. The redesign has optimized manufacturing and assembly as well as reduced costs. However, the production process can be further consolidated. Further improvements include compatibility to charge with existing EV charging networks and an accurate mapping of the charging networks in our mobile application. If we were to start fresh, we would further simplify complex parts on our board and consider adding varied powertrain and board style product lineups. With that said, thanks for your time. Please let us know if you have any questions or concerns.